we have a two-body collision here. And let's say we know that impulse is already force times time. So let's say that those two balls or cars or whatever the two objects are, they come to a collision. So let's say that car one is going to the right here, and then it impacts with car two, which is going to the right. Or going to the left. Car one's going to the right, and car two is going to the left. Now, mutually, both of these cars are going to apply an impulse on each other, but the impulse that they apply on each other is going to be equal and opposite. So, for example, car number one's impulse will be going to the right. So his impulse will be, let's say, force 1 delta t, because it's object 1. And then car number 2 will be negative F2 delta t. Why is the delta t's not 1 and 2? Because they impact in the same time. This is a collision that happens simultaneously, right? So this is, once you take the times out, this is reduces to Newton's third law. For every force, there is an equal and opposite force. Therefore, same logic. If for every impulse, there's an equal and opposite impulse, because the logic stays the same. You can see that in the equation form here, and the forces are equal and opposite. So force 1 right and force 2 left. Same amount of impact time. There we go. We can reduce to Newton's third law, but today we're talking about impulse. I'm going to take this impulse relationship and do something with it as far as the momenta being changed. Now, we also know that simultaneously when we have these impulses, right, that the momenta are going to be changed. The momentum of object 1 is going to be changed with respect to 2 and vice versa. We're talking about one object's momentum being changed as we do here. We're talking about a simultaneous change with two objects, right? So that's what we're going to be working with to break this down as much as we can. So therefore, let's go on. For example, so let's go with this idiom here, the idiom of Newton's third law, and then we can attack it with the impulse equation, or we can attack it with this Newton's law relationship. So let's choose that guy because he looks easier. So we know by Newton's second law that a net force is equal to sorry about that. The net force is equal to mass times acceleration, mass 1, and this is going to be A1 equals mass 2, A2, because this is the same equation for the force. For force 1 is going to be equal and opposite of force 2. So this is F1, and this is F2. Right, so, and in context, we can even say that's, for example, the force of 1 on 2 is equal to force of 2 on 1, or we can just, keep it as it's the same. So we're going to keep it this way. So let's break this down even further. So mass 1, acceleration is change in velocity over change in time, right? And this is going to be mass 2, delta V2 over delta T. Again, these impact times are the same, so we can just eliminate those. Right? So far, so good. You tracking this? Net force of 1 on net force of 2, simultaneous collision. The equal sign is the collision. This is where we have it. And now we have the change of impulses, respectively. So this guy was coming in, like say here, going in. 2 was going this way, like we see the balls coming in, C and D, and then there's a collision, and then let's say object 1 is going to go backwards, and then object 2 is going to go to the left backwards, and object 2 going back to the right. So it's like wherever they weren't going at first, the direction that the other was going first, they're now going to go in that direction, sort of thing. So F1 was going right, now going left. F2 was going left, now going right, that sort of stuff. Now let's continue. M1, delta V1, M2, delta V2. Okay, we know that change in velocity is final minus initial, right? So we have M1, VF sub 1 though, right? This is the basic, equation. Delta V is just going to be VF minus VI, but it's in terms of object 1. VF1 minus V1 initial, and that's going to be negative M2. Okay, VF2 minus, say, VFI, I want to say. No. VF2, sorry. VFI, VF2, not final initial, and multiply. All right, so there we have that, right? And so that's where our setup is. Any questions thus far? Everybody can see where this is going, why the most important thing is why I did all this, where I'm coming from. I'm coming from a collision. This collision is an impulse. This impulse applied here, this guy applies an impulse on that guy, simultaneous, a crash. In the same amount of time, I got rid of the times and I'm just left with Newton's third law. Those forces are these guys up here, equal and opposite. Break it down, simplify. That's all I'm doing so far. But,
Mr. Kelly?
period. Yes?
For the equation we just wrote down, the MVF1, isn't, for the second part, why is it two final velocities?
VF1, V2 initial.
Oh, it's okay. It's okay. I was just curious.
No, I know. I totally miswrote that. It's my bad. Yeah, I knew I was tripping on that. All right, V2 initial, VI2. That's what I wanted to write. Okay, yeah. So that's what we got. So now we can mess around with those even further because this is object 2, object 1. All right, okay. My fault. So let's expand this. And what we do is we have M1 VF1 minus M1 V1 initial. And that's going to be equal to, running out of space there, VF2. And this is going to be plus M2 V2 initial. So we have final terms, and we have initial terms. So let's combine the like terms. So we're going to have on the left-hand side, M1 V1 final, M2 V2 final equals M1 V1 initial, M2 V2 initial. So what we have here is the momentum, the initial momentum, all the i's together with all the masses, all the objects. We have two objects here. The momentum in the beginning, which is the sum of all the momenta of object 1 and object 2, and it could be any number of objects. The sum of all that momenta is going in the beginning is going to be equal to all of the momenta in the end. This is what is known as the conservation of momentum, because we are going to have the same before and after. We're going to save it or conserve it. So this is the derivation of conservation of momentum. Let me just now summarize that. Conservation And this is what we're going to pretty much be working with in the next rest of today and tomorrow. Sample problems mostly tomorrow. Okay, so let's make sure that we understand that. So I'm going to rearrange these terms. I like the initials to be first. Because they're initial. One initial. And that's pretty much it. I'm saving momentum before and after. The equal sign is the action, a collision. I hit and stick together. I hit and rebound. Some sort of verb, some sort of action is the equal sign that separates the beginning from the end. That's pretty much what we got. Any questions so far? All right, so let's make sure you have that. I'm going to access the textbook. I was going to do it up there, but okay. Two types of collisions. There's the perfectly inelastic collision, or let's say relative to that problem, or any problems of this type, really. So let's say we have M1, V1, initial. Let's say both of these objects were either at rest, could be at rest. Let's say that one of them was moving and the other one was at rest. It could be object one, object two, but then they will hit and stick. That's the equal sign, hit and stick together. That means that they're going to have a combined mass at the end, moving with one common speed. That's why this VF has no subscript, because they're moving together. This is a perfectly inelastic collision. For all types of collisions, since the system is closed from the environment, you're always going to save momentum. And I do the quotes because there's going to be some that's going to be lost due to some sort of sliding on the surface or whatever. Some heat's going to get lost. So for the most part, you're going to have the momentum saved, right? In an ideal situation. So momentum's always saved in all types of collisions, but the energy is not always saved. So for example, this is the collision, this is the equation that we're going to use for question one, perfectly inelastic collision. But the energy equation, let's say kinetic energy, because it's not in the air, it's going to be all kinetic. So 1/2 m1 v1 I squared, and that's not going to be equal. You can say the equal sign for the sake of argument, but it's not going to be equal in the end. The kinetic energy is not saved in these types of collisions. Okay, perfectly inelastic, because the masses, well, masses come together, they stick together and move as one. And the reason why is because some of the energy is going to be lost to heat, to the environment, the sound of the impact, screeching of tires. Those are all forms of energy being lost, let's just say, for the sake of argument, to keep it simple. So the energy is not going to be saved in these types of collisions in the perfectly inelastic world. But in an elastic collision, rebounding, we basically have the full conservation of momentum equation. So let's say that we had two objects. You have as many objects as we want. Okay, so that's what the equation is for the elastic collision case. We have two objects hit and they rebound. They're elastic. They spring off. They bounce, and that would be your equal sign. two objects come together, they hit, and they both move off at their respective velocities. So in these type of collisions, the momentum and the energy is saved. So 1/2 m1 vi squared. Run out of space again. So yeah, the energy and momenta are saved, whereas here, just the momentum is saved. So back to question 1, we're going to be basically using this. So every time you see a problem that says collide or hit and stick, they're combined together, or the phrasing is to that effect, you're going to use this first equation, the perfectly inelastic collision. In the real world, all of our collisions are in between. They're inelastic, meaning that when the objects hit, like for example, there's no such thing as an elastic collision in the real world, because when they hit, they're going to deform a little bit and then rebound. In an elastic collision, this is the ideal situation. They're going to hit and there's no deformation, there's no sound, and they bounce off. So for the most part, we just take the realistic situation in the world, which is inelastic collisions, and make them elastic because for the most part they are elastic. So let me amend that. In the real world, we have perfectly inelastic collisions. We can see that all the time in car crashes. They hit and stick and move off and cause all kinds of damage. But in the real world, we don't really have elastic collisions because we can't really model that. We can just use this as an approximation. So anyway, back to question number 1. Okay. Yeah. So we're going to use the perfectly inelastic collision formula for this to get the final speed. So it says, what is their final speed? They're going to be moving together as one unit. So 2 freight cars, each with a mass of 3 × 10⁵ kilograms, collide and stick together. Perfectly inelastic collision. One was initially moving at 2.2 meters per second, and the other was at rest. What's their final speed? Define the system as the 2 cars. Okay. All right, so usually have it over here. Okay. Let's say that the first car was initially moving at 2.2 meters per second. The other guy initially was at rest. So you want to find the final speed. So we're going to use the perfectly inelastic equation. So M1, M2, V final. So we're looking for that. So the second object was initially not moving, so we can get rid of that because 0 times whatever is 0. So it becomes an easier problem. So this is going to be M1, V1 initial, divided by M1 plus M2, because we're solving for V final. So we got to divide this over here, and we can put our stuff in. So this is going to be 3 times 10⁵ kilograms, 2.2 meters per second. So again, you can check the units. This is something for you semantically if you want to be technical. Make sure that your units of momentum check out, and the units of momentum are kilogram meters per second, and that's what we have. And then both of the masses are the same, so we just say 2 times 3 times 10 to the 5th, just double. And it turns out that it's very nice. So this guy can go away, and then it's basically 2.2 divided by 2 is 1.1. You guys see that? Which should make some sense to you, since they're the same mass, and when you double the masses, they're going to go half the speed. All right. So, you know, math matches our intuition. Any questions? So I guess give you some time to work on these problems. Now, again, notes or quizzes. I would like to have those problems as part of your notes. So please go to breakout, talk amongst yourself. If you have any questions, you know, pull me in. Don't just sit there. Just practice. If you're understanding this, you're good. But let me know if any questions at all. As a check for this one, why don't we see, for example, if the energy is saved or not in the perfectly inelastic case before I push you off. Okay, so let's see our claim, our hypothesis, if you will. Energy is not saved in perfectly inelastic collisions. So that means that our kinetic energy term right here should not be the same as the final. So we know that the initial velocity for object 2 is 0, so that term goes away. And let's just put our information in. 3 times 10 to the 5th, 2.2 squared, 1/2 right, and then this is going to be 1.1. That's the final speed, 1.1 squared. Now, of course, these 1/2s get canceled, and then we're left with just that. Okay. So 2.2 squared. So on the left-hand side, 1.4 times 10 to the 6 joules. And then, actually, we could have just canceled out 3 times 10 to the 5th as well, but anyway. Okay, so on the right-hand side, I pushed the buttons, right? So we have 7.26 times 10 to the 5th. So we lost a lot of energy here. 10 to the 6th down to 10 to the 5th. So not the same. So just a little check to make sure things work. And that's what we do in physics. We want to make sure that we test, we put the math framework down, a concept down. Now let's go to the lab. Let's test it out. See what we can see. Okay, so at this time, let's I'm gonna give you some breakout room stuff and come back in a little bit. All right. So this is question 2. We have hockey puck 0.105 kilograms. This is the first mass. He's put this down as V1 initial. And it's caught by the 75 kilogram goalie who's initially at rest. So this is a perfectly inelastic collision problem. M1 V1 initial. So we're looking for the final speed of the goalie. All right, so initially speed 0. .105. .24. And that should give us our answer there. Let's see if you guys got that. So again, this is going to be part of the notes. So make sure you have all that. So it should be 0.033 meters per second. So it's not move much at all. That should make some sense to you. He's got way more mass than the hockey puck, even though it's coming in at 24 meters per second. He's not going to slide back that fast. So that's question 3, or question 2, and then question 3. So a 35-gram bullet strikes a 2.5 kilogram steel ball that's at rest. After the collision, the bullet bounces backward at 5 meters per second. How fast? So now we have the elastic situation. So 35 grams, we're going to convert to kilograms, keep everything consistent. So we can just say 35 times 10 to the minus 3, just convert it to kilograms, or 0.0035. Mass 2, 2.5 kilograms. This guy's at rest. So after the collision, the bullet bounces backward at 5. How fast is the ball moving when it's back? How fast is the ball moving when the bullet bounces backward? So we have M1 V1 initial. M1 V1 final. And so we have the steel ball, V2 initial 0. Well, it bounces backward at 5. There's some missing information here. Let's see. After the collision, the bullet bounces back at 5. So V1 final, let's say, goes to the left at 5 meters per second. And so one other thing to keep in mind is that the directions do matter. So if the bullet was going towards the right at whatever speed, and you know, that's going to be a positive velocity, and then if it comes the other way, it's going to be negative. So the second guy's at rest. The only way we can really do this is if we treat it as a recoil, because there's no initial velocity given for the bullet. How fast is the ball moving? It bounces backward. Yeah, we can't really do it in the standard elastic collision form because we're not given an initial velocity of the bullet. We know that the steel ball is at rest. So the initial momentum in context with the information has to be 0 because we don't have the initial velocity for the bullet. So V1 initial must be 0. And then after that, we can figure out what the ball's speed is going to be after the so-called collision, because either they missed the information for the bullet, or it clearly is one of those situations where it's a recoil, but the context is off. Like for example, if you have an explosion, something's just sitting at first and then all of a sudden it explodes and you have two objects going in opposite directions, but this is not that type of problem. However, we don't know what the initial speed of the bullet is. So it's kind of tough if we do it in the standard way. Anyway, so the best way we can do this is the momentum in the beginning is nothing. And then we have the information for bullet and ball. So we have the bullet, let's say it's the first mass, M1 V1 final. So the bullet's going to have a V1 final of -5 if it goes to the left. And then now we have the ball speed as well. So we can solve it that way, because you can clearly see here there's no initial speed for the bullet, so they're missing information. It's awkward. So we can do this. M1 V1 final equals M2 V2 final. Run out of time here, but I'll set up the equation. V2 final is going to be negative M1 V1 final over M2, and plug in your numbers and you should get your speed of the ball. Yeah, sorry about that. It's a little awkward because the context is off for a explosion problem, and and they don't give you the speed in the beginning for the bullet, which is weird. But that's the setup. So, all right. So make sure you have all this. The notes. Turn in. I'll make a slot by 12:30. And we'll come back tomorrow and just do a bunch of practice problems and stuff. All right, so that's it. Take care. Have a good day.
Bye.
Bye, Mr.
Bye.
Kelly.
Hi, Mr. Kelly. Thank you.
Okay, sure.
Thank you. Have a good day, Mr.
Bye,
Kelly.
Mr. Kelly.
All right.
Thank you.
See ya. Yeah.
Oh, do we also have to turn this in?